Limits at infinity are some of the trickiest limits to evaluate. For example, here I have two limits of the same function, 3x minus 4 divided by the square root of x cubed plus 3. The first limit is the limit as x approaches positive infinity, and the second limit is the limit as x approaches negative infinity of that function. And so in general, when we want to evaluate a limit at infinity of a rational function like we have here, we have three basic guidelines that we can follow. The first guideline is that if the highest degree in the numerator is equal to the highest degree in the denominator, then the limit is equal to the ratio of the leading coefficients. The second guideline is if the highest degree in the numerator is less than the highest degree in the denominator, then the limit is equal to 0. And then thirdly, if the highest degree in the numerator is greater than the highest degree in the denominator, then the limit does not exist. And so if we look at our first limit here, where x approaches positive infinity, let's determine the degree of the numerator and the denominator. In the numerator, we have 3x minus 4, and so the highest degree is going to be found in our 3x term, right? The highest degree of x that I see is this x to the first power, right? So the highest degree in the numerator is 1. But in the denominator, we have the square root of x cubed plus 3. In this case, to find the highest degree, we need to look a little bit closer at the square root of x cubed. That is the same as taking x cubed to the 1/2 power, which if we multiply those exponents together, that is equal to x to the 3/2 power, right? 3 times 1/2 is 3/2. And so we can conclude that the highest degree in the denominator is 3/2. Now 3/2 is greater than 1, and so the highest degree in the numerator is less than the highest degree in the denominator, right? The denominator is greater than the numerator. And so if we go back to our guidelines, that lines up with our second guideline where it says if the highest degree in the numerator is less than the denominator, then the limit is equal to 0. And so we can say that the limit as x approaches infinity for this function is equal to 0, right? That will be the limit at positive infinity. But what if we were to look at the limit of that same function as x approaches negative infinity? The highest degree in the numerator and denominator isn't going to change, and so we might be tempted to say that, well, this limit is also equal to 0. However, we need to remember what values of x we are approaching in this limit. We're looking at the limit as x approaches negative infinity, but we need to make sure that this function is defined for values that would reach towards negative infinity. And so what I mean is, watch what happens if we plug in some negative numbers into this function. I'll start with -1. If we plug in -1, we'll have 3 times -1 minus 4, and that will be divided by the square root of -1 cubed plus 3. Now if we simplify this, we'll have 3 times -1, that would be -3 minus 4, and that would be -7. So in the numerator, we will have -7, and that will be divided by the square root of -1 cubed plus 3. Now -1 cubed is -1 because -1 times itself 3 times is -1. And so we have -1 plus 3, which is equal to +2. And so in the denominator, we will have the square root of +2. All right, so that is a defined value, but watch what happens if instead of -1, we plug in a slightly greater negative number of -2. Right, so let's do this again, except this time, instead of plugging in -1, let's plug in -2. So we'll have -2 here and -2 there. In the numerator, we have 3 times -2, that will be -6, and then if we subtract 4, that will give us -10, so -10 is in the numerator, and that will be divided by the square root of -2 cubed plus 3. Now, -2 cubed is equal to -8 because -2 times itself 3 times is -8, and then -8 plus 3 would be -5. So in the denominator, we have the square root of -5. But remember, we can't take the square root of a negative value and get a real result, right? This is equal to some imaginary number. And so this function is not defined for -2. And this would continue to happen for all values of x less than -2, right? Values that would approach negative infinity. This function is not going to be defined for those values. And so if we look at the domain of this function, right, if we determine what values of x this function is defined for, what we want to do is look at the denominator here and ask ourselves, what values of x would make x cubed plus 3 greater than 0, right? What would make this expression positive? And so if we have x cubed plus 3 greater than 0 and solve for x, that will tell us what values of x our function is defined for. And so if we subtract 3 from both sides of the equation, we'll have x cubed is greater than negative 3. And then if we take the cubed root of both sides, we will find that x is greater than the cubed root of negative 3. Now, if you put the cubed root of negative 3 into your calculator, you'll find that that is approximately equal to negative 1.4422. And so what we find here is that for values of x greater than negative 1.44, this function is defined. Anything less than this value, meaning negative 1.45 and negative 2, negative 3, all the way to negative infinity, this function is not defined for those values. And so because of that, because the domain of this function is values of x greater than negative 1.44, it's a bit of a ridiculous question to ask what is the limit as x approaches negative infinity, because this function doesn't approach negative infinity. It just doesn't. It's not defined for values that get closer and closer to a larger and larger negative number. And so because of that, we can't conclude that the limit as x approaches negative infinity of this function is equal to 0, like the limit as x approaches positive infinity was. Right? This function is defined for values that approach positive infinity. You can continue to plug in greater and greater positive numbers into this function. It's still going to be defined. And so we are allowed to conclude that this is equal to 0 using those guidelines. But for the limit as x approaches negative infinity, we cannot make the same conclusion. And so we have to say that the limit here does not exist. Right? The limit can't exist at negative infinity if our function doesn't even approach it at all. And so it's going to be important for you to look closely at the function in your limit if your limit is approaching negative infinity. You need to make sure that it is defined for those values. Now, I want you to compare the limit of this function to a very similar function. Here we have the limit as x approaches positive infinity and x approaches negative infinity of the same function, except we have x squared in the square root in the denominator rather than x cubed. And this makes all the difference. This function here in these two limits is defined for all values of x, right? Because now if we plug in negative values into x squared, well, they're all just going to become positive. And so if we add 3 to them, it's still going to be positive. And so the denominator will always be a real result because we're always going to be taking the square root of a positive value. It's not going to be negative. However, taking the limit as x approaches negative infinity of this function is still a little bit tricky, even though it's defined for all negative values of x. Another thing to remember about limits at infinity or negative infinity is that that limit actually tells you where a function has a horizontal asymptote. But for this function right here, if we were to look at its graph, it actually has 2 horizontal asymptotes. And this is because of that square root of x squared in the denominator. And that would also be the case if it was found in the numerator. But the reason that this occurs, that there are 2 horizontal asymptotes, as opposed to just 1 horizontal asymptote, like the majority of functions that you will come across, is because of the behavior of the square root of x squared. Right? Another way to write the square root of x squared is to say that it is equal to the absolute value of x. And that is because no matter what value of x you plug into this function, you're going to be squaring it, which will make it positive, and then taking the square root of it will output the positive result, right? So even if I plug in negative 1 for x, negative 1 squared is positive 1, and then the square root of 1 is 1. And so even though we plugged in negative 1, it outputted positive 1, and so the square root of x squared is essentially the absolute value function. And then remember that the absolute value function can be defined as the following piecewise function, where you have positive x for values of x greater than or equal to 0, and negative x for values of x less than 0. And it's because of this definition right here of the absolute value of x, or the square root of x squared, that this function has 2 horizontal asymptotes, one in the positive direction and one in the negative direction. And so when you look at the limit as x approaches positive infinity of this function, you're only finding the limit, or the horizontal asymptote, in the positive direction. You would find that this limit is equal to 3 because that's where that horizontal asymptote is located. But if you look at the limit as x approaches negative infinity, you are looking at this horizontal asymptote instead. However, if you were to solve these two limits, as we solved one of the previous limits by using those guidelines, you would get the same answer for both of these to be equal to 3. But that wouldn't be correct for this limit as x approaches negative infinity, because the actual limit as x approaches negative infinity is negative 3. And so what has to happen here is when you evaluate a limit at negative infinity, for a function like this that has two horizontal asymptotes, you need to multiply the square root by -1 so that you can look at the negative side of the function, right? Instead of looking at the positive values of x, where x is greater than or equal to 0, we're looking at the negative values of x when x is less than 0, right? X is approaching negative infinity, and so we're looking at the negative values of x. Okay, so that's why it's important to add a negative sign in front of the square root of a rational function where the limit is approaching negative infinity. But now, as a comparison, I want to show you some graphs of other rational functions that you could potentially take the limit of as x approaches negative infinity. And so here's the rational function that we started this video with, right? We looked at the limit at positive infinity and negative infinity for 3x minus 4 divided by the square root of x cubed plus 3. This is the graph of that function. It only has one horizontal asymptote at y equals 0. And this makes sense because if you look at this function as x approaches positive infinity, it is approaching 0. But if you go in the negative direction, there's going to be a vertical asymptote, which I don't have labeled for this graph, but it would be there, of the cubed root of -3, right? When we set x cubed plus 3 greater than 0, we solved for x and found that x was defined for values greater than the cubed root of -3. And so that's where that vertical asymptote would be. And so because of that, our values of x do not get larger than that value. They simply get closer to it, and our y values decrease. That is why the limit does not exist, because this function is not defined for all those negative values. Okay, but then if we look at this other function here, this is very similar to this previous function, except instead of having a square root in the denominator, we have a cubed root in the denominator. And what I want you to notice here is that even though we have the cubed root of x cubed, we still only have one horizontal asymptote. Sometimes students will think, well, since the square root of x squared produces two horizontal asymptotes for a rational function, then maybe the cubed root of x cubed will as well. But as you can see here, that is not the case. And that's because the cubed root of x cubed doesn't work like the square root of x squared. It's not the same as an absolute value function. If you plug a negative value into x cubed, such as -1, that value cubed will still be negative, right? -1 cubed will be -1. And then the cubed root of that will still also be a negative value. And so that's why this function will still have one horizontal asymptote. It's not going to have two different asymptotes for the positive and negative sides. Both sides are going to share the same asymptote. Next, I want you to look at this function here, where we have a very similar function once again, except in the denominator, we have the fourth root of x to the fourth power plus 3. Now for this function, we once again have two horizontal asymptotes, one at positive 3 and one at -3. And so if you had a limit as x approaches negative infinity for this function, you would need to remember to multiply by that -1 so that you will look at the negative side of the function and get that other horizontal asymptote, right? And that would be because just like the square root of x squared produces only positive values, the fourth root of x to the fourth power will also only produce positive values. It will not make a negative value, and so the denominator will always have a real result. But then as a comparison, look at this function here. We have the same function as we have up here, except instead of the fourth root, we have the square root of x to the fourth power. And now once again, we only have one horizontal asymptote, not two like we had before. And so even though we have the square root of x to the fourth power, which is always going to be a positive value, right? Notice that this function is defined for all negative values and all positive values. It still only has one horizontal asymptote at y equals 0. And so in general, here is what you need to know about limits at infinity for a rational function that includes a radical in the numerator or the denominator. If you see the nth root of x to the nth power, where n is greater than or equal to 0 and n is even, meaning numbers like 2, 4, and 6, then you can expect to see two horizontal asymptotes for that function. And so if you're looking at the limit as x approaches negative infinity, you need to remember to multiply by -1 for that limit. Remember, the nth root needs to be the same as the power of that function, right? So this can't be 3 and this can't be 2. These need to be the same in order for this to hold true. You have to have the square root of x squared, or the fourth root of x to the fourth power, or the sixth root of x to the sixth power, and so on. But if n is odd instead of even, then you can expect one horizontal asymptote. And so that would apply to the cubed root of x cubed, or the fifth root of x to the fifth power, and so on. And then if the root n and the power n do not match, then you can expect just one horizontal asymptote, right? So if you had the square root of x cubed, or the cubed root of x squared, you're only going to see one horizontal asymptote, and so you don't need to worry about multiplying by -1 if you have a limit at negative infinity. Right, and so that's what you need to remember for limits at negative infinity for rational functions that have a radical in the numerator or denominator. But of course, if you are ever stuck and you're not sure what to do, and you have access to the ability to graph the function, whether that be in a graphing calculator or you're somehow able to graph it by hand, I would always recommend that you look at the graph because that will always help confirm how many horizontal asymptotes a function has. Alright, and so that is all I had for this video, and so if you have any questions, feel free to leave those in the comments. But if you don't have any questions and you found this video to be helpful or you enjoyed it, feel free to check out some of my other calculus videos that you can find on the channel. But that's all I had for now, so I will see you next time.